So in this video, we're going to sketch the graph of the given function f of x equals the cubic x cubed minus 6x squared plus 15. And we're going to use the key ideas from 3.5.1, the Clark way we talked about in another vehicle curve sketching. All right, so those 8 things there. So want to show all work, so this is what you're expected to do. So number 1, I want to find the domain of the polynomial f. Well, guess what? Since it's a polynomial, we know that the domain is all real numbers, negative infinity to positive infinity. Okay? Pretty easy. All right. Now, this number 2, we're supposed to find the critical values of f. To do this, I take the derivative. The derivative of x cubed is 3x squared. The derivative of negative 6x squared is negative 12x. Derivative of 15 is 0. Once I get the derivative to find critical values, I figure out where it doesn't exist and where it's equal to 0. Well, this is a quadratic, so it exists for all real numbers. It's a polynomial. So I need to set this equal to 0, solve for x. If I do that, then I can factor 3x out of each of these terms. That's going to leave me an x for the first one and a negative 4 for the second. Okay? So I'm going to set each of these factors equal to 0. If I set the first factor 3x equal to 0, then I just get x equal to 0. And if I set the second factor x minus 4 equal to 0, solve for x, I get x equals 4. Okay. These numbers here are the critical values. Now these critical values are potential relative max or mins. We'll see. Now number 3, I need to find the possible points of inflection. So POI, points of inflection for the function. That means I need to take the second derivative. The derivative of 3x squared is 6x. And then the derivative of negative 12x is just negative 12. And once again, this thing, set it equal to 0, or where it does not exist, it's a line, so it exists everywhere. So we're just going to set the second derivative equal to 0. To solve for x, the first thing I do is I'll add 12 to both sides. So I have 6x equals 12. If I divide by 6, I get x equal to 2. So this is my potential point of inflection. Now that I've completed number 3, I'm going to move on to number 4, finding all vertical asymptotes. Well, since this is a polynomial, domain is all real numbers, I have no vertical asymptotes. Pretty easy. What about number 5, horizontal asymptotes? Well, I need to take the limit as x goes to negative infinity. Well, let's think about cubic. Cubic, all that matters is the degree of the term, which is 3, and then the coefficient in front, which is positive 1. So from college algebra, you learned that cubics with a positive lead coefficient, right-hand behavior goes up to positive infinity, left-hand behavior goes down to negative infinity. So this is the left-hand behavior. What happens as x goes to negative infinity? Our function goes to negative infinity. So there's no horizontal asymptote on the left side. And same thing for the right side. As x goes to positive infinity, this lead term grows without bound. And so this goes to positive infinity here. Now, no horizontal asymptotes and no vertical asymptotes is what we've just proven here. So let's move on to number 6. Create a number line that has critical values, points of inflection, vertical asymptotes, and for each subinterval, determine where we're increasing, decreasing, concave up, concave down. Oh no. Okay, that's going to change things. All right, so I'm going to need to write for the rest of that because now I just accidentally locked my ability to go backwards out. So, okay, this would be fun doing this with a hurt finger. All right, now for this subinterval here, I have a -1 value and a 1 value here and a 5 value here. Those are points in between. So I'm checking points in between just to see, what the first derivative will compute to. So we know that the first derivative is going to be 0 here based off of what we found in this information right there. So whenever I plug in f prime of -1 here, well, what is f prime equal to? It's 3x times x minus 4, right? So that gives me -1 times 3 is a negative number times, -1 minus 4, that's a negative number too. And so a negative times a negative equals a positive. And so that means that on this interval we're positive, so we're increasing. Okay, at f prime of 1, what's happening here? Well, when I plug a 1 in, I have 1 plugged in here, gets me 3 times 1, which is a positive, and then 1 minus 4 is negative. So that gets me a negative, so we're negative, negative, negative. That's decreasing here. Okay, and then f prime of 5, is going to be, well, 5 times 3. What's that get me? That actually gets me a positive 15, and then 5 minus 4 is still a positive 1, so that's positive there. So we're positive, positive, positive derivative. That means we are an increasing function at that point right there. Okay? So, what does that tell me? If I'm going up and then I turn to go down, that's a relative max. So I have a relative max at what? At x equal to 0. And then if I'm going down and then I turn to go up, that means I'm going to have a relative min at x equal to 4. Okay? Now that handles where we're increasing, where we're decreasing. Okay, what else do I need to do? I need to figure out where we're concave up and concave down. So that means I need to focus on the second derivative. So I'm going to draw another number line. Okay, so we've got one at 2. Now we know at 2 that it's a second derivative is equal to 0. We knew that already. So I need to find critical points on both sides. So pick a number smaller than 2, I pick 0. Pick a number bigger than 2, I pick 3. So if I plug in f double prime of 0, what do I get? Well, if I plug in 0 here, I get 6 times 0 is 0 minus 12. That's a negative number. Okay, so negative, negative means I'm concave down. I'm sad, right? Okay, and then over here, if I do f double prime of 3, if I plug in 3 here, I get 18 minus 12 is a positive number. So I'm positive, so I'm concave up like a cup, right? Okay, so looks like I have a change in concavity at 2. Is the function defined at 2? Well, what do we know about this function? It's defined everywhere. It's a polynomial. So I actually do have a point of inflection. Okay, so my point of inflection, POI, is at x equal to 2. Okay, point of inflection, x equal to 2 here. Okay, so what's next? Well, I want to evaluate each critical value and point of inflection, figure out the locations. Okay, so how do I do this? Well, I need to work my way through it. So the first one is relative max at x equal to 0. I need to know what f of 0 is. So I'm going to do 0 cubed minus 6 times 0 squared plus 15. That's easy. That just gets me 15. So 0 comma 15 is my relative maximum here. Next up, I have f of 4 for my relative minimum. And when I plug that in to my original function, like I just did for f of 0, I'm going to get negative 17. So that tells me that 4 comma negative 17 is the relative min there. What else do I have? So this is a relative max. This is a relative min. And then point of inflection, x equal to 2. So that's f of 2 equals, if I plug that in, I get negative 1. So that's a 2 comma negative 1 for point of inflection. Okay, so that kind of summarizes up everything right there. Okay, what else do I want? Well, once I plot these points, I want to plot them along with the x-intercepts and the y-intercepts. So if you'll recall, to get an x-intercept, what I need to do is I need to set y equal to 0. Set y equal to 0. So here in this case, f of x is y, so 0 equals x cubed minus 6x squared plus 15. If you can factor that, you're better than I am. I don't know how to factor that, so what I'm going to do is go into my calculator and type in the function. So if I type into the function, excuse me, x cubed, and then minus 6x squared, and then plus 15, and hit enter. I see that I've got 3 roots, so I'm going to calculate these roots. Second calc, zeros. And so I'm going to go on the left bound, I'm going to go on the right bound, and I get a 0 at negative 1.4. Okay, I need to do it again. Second calc, 0. I'm going to go on the left bound and the right bound, and I get 1.9. And then I do it one last time. Second calc, 0, left bound, and then right bound, and I get 5.5. So my x values, it's okay if you approximate here 1 decimal, whatever I tell you how many decimals to approximate, you just do that. So negative 1.4, 1.9, and 5.5. I'm going to say from the calculator, so I know like where this came from. I didn't factor it, okay? I also want the y-intercept. To get a y-intercept, I'm going to set x equal to 0. So everywhere I see an x, I'm going to put a 0. So that's 0 cubed minus 6 times 0 squared plus 15. Hey, look, we already calculated this. So this is equal to 15. So I have a y-intercept at 0, 15, okay? And here's all my x-intercepts. So now all it amounts to doing is graphing it. So what I'm going to do here is I'm going to kind of shrink this information up. Since I freehand wrote it, it's a little smaller than it should be. So let's shrink this up. Okay. And that's going to give me more room to do my graph. All right, let's see if I can add, let's do a sticky grid. Oh my goodness, the benefit to having the notes pre-done when you have a broken finger are amazing. Okay, so let's make our cubes a little smaller. All right. Hopefully that'll be good enough. So what I'm going to do here is I'm going to count by ones here. So that's -1, -2, -3, and so on. Over here, I've got 1, I've got 2, I've got 3, 4, 5, 6. Okay, I think that's good enough because we had x-intercepts 5.5 and -1.4 is the other range of that. Now, I have a y-intercept of 15, so that's going to go up pretty high. So I think I'm going to count by 2's here. So 2, 4, 6, 8, 10, 12, 14, 16. Okay. And want to go down 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's -18 down there. Okay. All right. Now, and then that's -16. Okay. So let's see if we can put everything together, because I needed to go down to -16, up to, or 17, and then up to 15. So I think I got it now. So let's plot our points. Let me move these down here where we can see them better. Okay. All right, so -1.4 is an x-intercept. Okay. 1.9, which is almost 2, is another x-intercept. And then 5.5 is another x-intercept. So we can label these. So -1.40, and I'll want you to label them on your test for sure. So, and then 1.9, 0 there, and draw a little arrow out here, 5.5, 0 there. Okay, so those are my x-intercepts. I'm going to do a different color for y-intercepts. So y-intercept, we just have 1, it's a function, right? So this y-intercept is at 0, that is not 15, here's 15, 0, 15. And it turns out that that's also the relative max there, so that's the highest we're going to be. Okay, so that's like a 2 for 1. Also, we have 4, -17, so I go over 4 and down -17. So that's like right here. That's a relative minimum. So 4, -17, that's my relative min. Relative min. Relative max. See how I'm labeling all these things? What about, I think that's it, right? So 1, 2, 3, 4, 5, 6, and then this one is a repeat. 1, 2, 3, 4, 5. Oh, we need point of inflection. Okay, point of inflection. Our point of inflection here is 2, -1. So that's like right there. So 2, so that's kind of like right by the 1.9, 0. This is my point of inflection. Point of inflection, 2, -1, right there. Okay. So very important that you label them so I know, what's what. So label your relative max, your relative min, your points of inflection. Intercepts are okay, unless, that intercept happens to be a relative max, min, or point of inflection, right? So now what I want to do, that I've got all the points, I've plotted all the points, I want to connect the dots with the appropriate concavity. So looking at this graph, I kind of know like the general shape of that graph, right? I kind of know that's what it's going to do. But how do I know that for sure? Well, this is what tells me, okay? On the interval from negative infinity to 0, I'm increasing. Okay, from negative infinity to 0, I'm going up. All right, I know I'm going up. And then from 0 to 4, I'm actually going down. Oh, come on. Is my thing frozen? Get out of there. Hey, come on now. Goodness, my iPad is just messing up on me today. Okay, here we go. So 0 to 4. So we're decreasing 0 to 4. So 0 to 4 range, it's on the decreasing slope. Okay. And then from 4 to infinity, we're increasing again. That's what we know from the first derivative. Now the second derivative tells me that I'm concave down, okay, for less than 2, and I'm concave up for greater than 2. So at 2, I switch concavity, okay? On the 2 side, I'm concave up. And on the less than 2 side, I'm concave down. Right? So this is going to help us in drawing our curve. Right? So I'm not expecting you to have highlighters and doing all this stuff. But here we're increasing, right? So as we come this way, so as we're working this way, we're concave down. So you can kind of see how the curve is concave down here. So we're going positive, increasing, right? So our function is increasing from negative infinity to 0. But we are also concave down, so negative on the second derivative side of things, okay? Now here we switch gears, okay? And we're decreasing, and we're still concave down. So we're decreasing and we're concave down till we get to 2. Okay, so let me pass through. Okay, so it's kind of hard to see this, okay? But we are concave down here. So if you're having trouble, like if you're having trouble drawing it where it looks like it's actually concave down, you know, you need to make it to where I can tell what you're writing as concave down. So you can say like here, like, okay, this one is decreasing, obviously, and then the concavity is negative still, so I put the negative on top here, okay? So that's the concavity. All right, and then this side is telling me that it's decreasing. And this is telling me I'm increasing. And this is telling me I'm still concave down. So if you want to write that on there so that I know what you're talking about, like you're having trouble drawing it, you know, being an artist isn't quite your thing, then you need to write it out so that I know what it is and you're not just putting straight lines. If you put straight lines, you're going to lose credit for the concavity part. Okay, so here, all of a sudden, we're still decreasing, but the concavity changes to be positive. We're concave up. And so like a cup, it comes like this, right? Okay. And so what does that mean? Well, I'm still a decreasing function, okay? but my concavity changes to be positive now. So I'm putting plus signs because I've got pluses there. Okay. And then I'm still positive concavity, but I'm going up. Okay, I'm going up like that. All right, so I'm going to continue my positives because I'm concave up from here on. Okay, from here on, you're concave up like a cup. From there back, you're concave down like a frown. Okay? All right, and then we change from decreasing here to increasing here. All right, so all along, I'm using this information that I found right here to help me graph, because you can see right there we're increasing from 4 to infinity, and 2 to infinity we're positive. Second derivative, which means concave up. So this is my graph. Okay, you can, maybe I will highlight this so you can kind of see it better, what the graph overall is looking like. Okay, so once again, sorry about slipping up and losing the written out video, but you know, that happens every once in a while, so it's good to see a mistake.